Okay, good, let's start. So only one lecture this afternoon, and the lecture is about cost semantics. So this is something that came up a few times now already. So yeah, you said like, oh well, you know, how do you do that, and is that efficient, and what are the difference between call by name and call by value? And so the topic is like, how do we efficiency in the semantics, and this is what the cost semantics does for us. And then I was wondering, okay, what use is PCF? And we have seen almost all the ingredients to it, except the fixed point operation that it has. So it's something like the Y Combinator, but built into the language. So that's the only additional ingredient that we need. So I thought we'd just go ahead and use that. And so I will start with defining what PCF is. So what does it stand for? I think it stands for Programming Computable Functions or something like that, which is a weird name. It was invented by Plotkin, I think, as a tactic language for a theorem prover that they were developing, and it's a very small language, that has a general recursion that is Turing complete, and it's sometimes called the E. coli of PL because it's like often used to study things and like isolation and kind of like a well-known setting. So that's what we're gonna do too. So let me just say PCF. It's by Plotkin. So, and it's a small language. It's general recursion, and the way the recursion is defined is like with fixed points, and this is something that came up a few times already. I just want to repeat it. So you have seen the combinator already, the fixed point combinator, and in general definition. So if f is a function and f of small f is small f again, and we call small f a fixed point. Okay. So why are they related to recursion? So, and you've seen that already. So just do an example to bring that out again. So let's do a factorial. So there are three ways to look at that. So first of all, that like operate. Now we can take an operation of, and we say, okay, factorial is defined as follows. Well, f of n and then we have a case. So either it's if n is 0, or it's 1 if n is greater than 0. Yeah, but I'm running out of the that's the only one I have of these good ones. I can try the regular one. So why is that an operational view? Well, so if we have, f of kind of like, replace it with its definition, and you can say like, oh well, so then, we are like in this case, I can unfold the definition, so this is 2 times f of 1, and then I can unfold the definition of 1, right? So this is 2 times 1 times f of 0, and this is 2 times 1 times 1, and this is 2. Yeah, so that's probably the way you would think, like, of a recursive definition. But we also can think of it like differently. So we can think of it like, how did I call this? Well, just, as an equation. So, yeah, we can view this, here this is supposed to be equal. So we can view this as an equation that we want to solve. So we have, like f as a variable now, and we want to find like a solution to an equation that looks like that. So f should be function that takes a number n, and then, if f equals 0, then 1, else n times f of n minus 1. Yeah, and yeah, you can show that, for instance, so what we want is, let me say this first, so find solution f to this equation. So for example, the like successor 2 function, or successor twice. So, which is this function, so this is not a solution, right? If you plug that in for f, you have a different thing on the left than what you have on the right, right? Because like on the left, if you, plug in 1, you get 2, and here on the right, if you would plug in, or let's say, if you plug in 0, I want to say you get 2 here, and if you plug in 0 here, you get 1. So that's not a solution, so it's not a solution. And the factorial function is a solution. Yeah. So if you plug that into this equation, you get the same thing on the left and the right. So that's like a a different way of looking at recursion. You define an equation, and you want to compute a solution to the.
You have written equation for factorial, right?
Yeah.
But you are trying to use that in successor 2.
Right. I'm just saying, like, you can plug in things for f. You can see if this like equation is true or not. right? So if you plug in the successor, if you replace, substitute the successor in for f, so then, what you have on the left-hand side is not what you have on the right-hand side. But if you plug in the factorial function, then what you have on the left-hand side is the same what you have on the right-hand side. So that's kind of like different way of, looking at the recursive definition. And then the third way is almost the same thing. And that's how we go into PCF. And what you've already seen in the lecture about the lambda calculus is so here we just write basically the same thing as like this equation. We just say like it's a function that takes f and returns a new function that looks exactly like what's written there at this equation. So if n equals 0, then 1, else n times f of n minus 1. And then the point of view is, so we are looking for a fixed point of big F. So and factorial is the unique fixed point. So this is something you could prove, but we're not going to get into that. So there's only, there could be multiple functions that, satisfy such an equation. And in PCF, this is actually true. There are sometimes multiple functions that satisfy such a recursive equation. But I can say a bit more about that. But this is kind of like, the general so that's the point, the viewpoint of PCF. So we have an operation that can take fixed points. So, and that's the only thing that's new, and I'm of course going to show you how that works in a second. Yeah. Oh, question. Yeah. Yeah, right. Yeah. It's, all three cases, it's the same thing. It's just, different ways of looking at it. Yeah. Okay, questions here?
You said PCF features an operation fixed point of big F. Does that mean fixed point of?
No, big F is not a fixed point, right? Big F is just. No.
Okay.
Right, so, you can write this down. That's a higher order function you could write down in ML. Fixed point operation then big F and returns you a fixed point. Excuse me. Switch back to this one. Okay, so let's define PCF. So the types, I just write them down for completeness. So we have the natural numbers, and we have functions. So here I follow the notation in PFPL, and I don't call it arrow, I call it partial arrow, just to emphasize that these functions might not terminate, to remind us of that. But that's a detail, not too important. So now the expressions. So what do we have? We have variables, and we have natural numbers that you've just seen in the last lecture with zero and successor. Then we have the conditional, like this. Conditional for the natural numbers, which has like the zero test built in. So yeah, so that's actually something new. So that's not what you've seen. So that's you've seen this like recursor, and here this is just a test for zero. And if it's not zero, then you get the predecessor out, and yeah, you can use it. You bind it to the variable x, and then you can use it in the E1. So that's how that one works. And yeah, why is you gonna ask me again? Yeah, why are these like curly braces there? So you can also write it differently. Not so important. So let's just write it like this. Okay, so then and so this is like all stuff you know. Well, I mean the conditional here is a little bit new, but maybe already now you know how to define the statics and dynamics for this. So, but what's new is this fixed point that to give you the concrete syntax. X x of type tau is E. Yeah, this is our general recursion. So if, to give you already like before defining the statics and dynamics, I want to show you how you use this. Let's do an example. Okay, so the factorial function. This means like is defined as. So it's a recursive function. So it's a fixed point, and it's a function from natural numbers to natural numbers. So I write the fix f is supposed to have type not partial arrow not is, and yeah, can, like in this equation before, so this is kind of like the argument of our function big F. I can now define what the function is. So in the function x, a natural number, and then we use our zero test. Yeah, maybe I also should have given you the concrete syntax of that one. So that looks as follows. If 0 E, so case, yeah, if it's 0, then we do E0, and if it's at X, then we do E1. Yeah, this is a concrete syntax for that one. So then here we want to branch on X, and if it's 0, well then we want to return what? 1, I think. So that's this. And if it's as of, well, I have to use Y now, then we want to do what? We want to do X times F of Y here. Yeah. So that's how you define the factorial function. So it's just like a syntax for that. And the fix means, oh yeah, well, take the fix point, of this. Well, you can view it as an equation, or you can say like, well, you have this, big function f, so that's why we call it fixed point. It doesn't really matter. And if you know SML or Haskell, so then, basically this is like if you define a function, usually, I think in Haskell you can basically write it like that. So in Haskell, every definition you write is automatically recursive, I think. Yeah. So there you can basically write the same thing. Almost. Okay, so now you're of course curious, what is statics and semantics? Yeah.
What is that operator
Oh, this here. Oh yeah, that's outside the language. I'm just saying that's a definition. Yeah. That operator doesn't exist. And we also don't have multiplication really. Yeah, so there was a little bit of cheating there. But just, to illustrate it. Okay, so statics, what do I want to show you? So as a warm-up, we can do the zero test. It's conditional. So if I wanted to have type tau, so what do I need? So what should be the type of E to start with? Right? So in the same context. So what should be the type of E0? Tau, exactly. Yeah, so what should be the context? Gamma. So what should be the type of E1? Tau, right? and x is in the context, and what's the type of x? Not exactly, because it's a predecessor. Good, yeah, you're good. You don't need me anymore. So now, let's see if you can. So what should be the type of the whole thing, of the fixed point? Nat, tau arrow tau. Well, look at this example here. Here our tau is not arrow nat. So now I said that fixed point defines like the factorial function in the end, which should have net arrow nat. So here the type of the whole thing is just tau, which there was net arrow nat, but here it's tau. So we don't have to have any restrictions. You can by recursion function type an arrow, but it doesn't have to be like that. So if you, for instance, have the lazy natural numbers that you talked about before, so you could also like use the fix to create an infinite natural number. So then like if you have like the lazy natural numbers, they're not really the natural numbers because you also have like infinite in there. But this is something you could create with a fix. But of course, like the E in there cannot be arbitrary, right? So the E has to be somehow related to this type tau. And in what way? I mean, if you look at our example, it's also again the same type tau. The interesting part is, what is the context of it?
X is also type tau.
Exactly, X is also tau. So that's how this whole thing works. So you assume you have it already, and then you say what it is. So that's a fixed point. And now you're curious what can be the dynamics of this. That must be extremely complicated, but it's not. So I'm not giving you the dynamics for the if zero. Well, I give you maybe one rule, so you see it's nothing new. Just as a warm up again. So you're probably already able to define that yourself. So if you have the zero test, what should you evaluate first? Exactly. E, until you have a value, and then you check what it is, and then you either move to, oh, I forgot the X here, sorry. You either move to the E0 or to the E1, depending if it's zero or successor. So that's easy. But the interesting question is this fix. So this seems to be rather strange. So if you look at the factorial function here, so yeah, kind of, what do you want to do with it if you see it in the evaluation? I mean, you almost have the right thing here. Oh, never close these curly braces. So you almost have the right thing already here. The only thing is, like, so you want to basically say, like, oh, well, it should be something like, you know, this function there, but you have this f lingering here that, you know, you don't know what to do with it. So if we translate it to the situation over here, so you basically want to say, well, it's E, but E now has this variable x in it that, you know, refers to it, the, you know, thing already. So what are we going to do? We have to substitute. What can we put in? What do we have? So we really don't have much. So, well, we have E itself, but it doesn't seem to be the right thing. So we put in the fixed point itself, the whole thing, or the fixed expression itself. So then you say, like, oh, well, this seems to be a bit strange. Doesn't that mean, like, it never terminates or something like that? But look what would happen here. So if you want to make a step with a factorial function, well, so you would take, you know, the whole fixed thing, you plug it in here for f, and then you have a lambda, then you have a value. So you just, you know, it does exactly the right thing for you. You want it to be a function, so you make a step. Well, it is a function, you know, with a lambda. So you don't make any further steps anymore unless, you know, you want to apply it to an argument. Then, of course, you know, you can make further steps. But if you apply it to an argument, so then what will happen, like, either you go into this branch if it's 0 and you're done, or you go into the other branch and then you do something here, and then you have the recursive call. And then, only then, you know, this, like, fixed rule at some point gets triggered again, and then you know, unroll, go through it. So that's how this works. So yeah, that's a good homework to, you know, just apply this factorial function to, like, 2 or whatever, you know, and do the steps and see, you know, where this is going and how this evaluates. Okay, that's something I wanted to say earlier. So for the finite data types, of course, we can always prove our type safety theorem, right? So progress, meaning if it is well typed, type tau, then either is value or I can make a step. Right, so that's, write it down again. I mean, you know it already. Doesn't hurt to have it on the board a couple of times. So if E is well typed of type tau, and I make a step to some E prime, then prime remains well-typed of the same type. This is true for, you know, the language E we had at the beginning. This is true for the language types, and this is also true for PCF. Yeah, question.
Just about dynamics in general. When we list these, we're like skipping a lot of like the extremely boring ones, right? Because like, you know, everywhere where there's an E, you could say like, well, E steps to E prime, therefore, you know, like there's several that have been written down because they're too obvious to bother. Or at least really the only dynamics.
No. I mean, of course not. I mean, so there, I have to say what the values are, right? But you know all these already,
Sure.
right? I mean, you know the rules for the natural numbers. You just have seen them in the last lecture. You know the ones for function application. You know the one for function abstraction. It's a value, and these you know. So I only give the rules for the new constructs, and here for this one, there are 3. I didn't give you 2 of them, and this just had this one. Yeah.
To back up real quick, just to like fix and stuff. Like I get the dynamics of this, and I get what, you know, for factorial 2, the values 2 and stuff. But like, what is this like telling us and stuff? I don't know. I guess I'm confused. Like, where does it come into play here? Like, I don't know. It's
So why is it interesting?
yeah.
Oh.
I would say that because that's the way I feel. I think maybe you feel the same way.
Yeah, like I get that we're introducing fix here, and I get that.
Oh, it's just, yeah, right. It's just like,
Like why
What?
are we specified on factorial specifically?
oh no, factorial is just an example.
Okay.
So the fix you can use, you know, to now define the factorial, but also other. I'm just saying, you know, for the thing I want to do now, also the thing I want to do in the next lecture, I have to use programming language. Didn't want to use, you know, potentially cannot terminate. I didn't want to have full recursion. Well, I just use PCF, which is also, you know, interesting to you guys because, like, you know, that's what people usually do. You know, if you want to start something in PL, you use, you know, you add it to PCF. Start with PCF and you add it to it, and so it's good to have the PCFs. So that's the only reason we're looking at it, and now I want to do my cost semantics for it. Yeah.
Clearly you get the list because I must remember fixed points. We try to find like roots of equations or something, some iterative process. And here, I get that this must be useful in semantics some way, but I feel like you already gave the solution. You wrote the same formula there, basically, for the factorial in all the different in the operational as an equation and as a fixed point.
Oh yeah.
The same thing. You're
Right.
already giving the answer. So how is this interesting?
No. Well, I mean, it's in some sense not interesting. I'm just telling you why people call this a fixed point operator, right? And in semantics, yeah, that's, you know, like if you have a denotational semantics, you know, that's, you know, the way they view it. But in our case, with like this rule here, with our dynamics, we have an extremely operational view to it. And, you know, it's just like, you know, the whole point with it was, you know, like, why do people call it a fixed point? Because you can view it as a solution to this equation or to a fixed point of this function. It's the only reason people, you know, call it a fixed point, and that's basically what the fixed point operation does. But here we have like a very operational view, so you don't, you know, have to think about it too much. So know how this works in the dynamics, so that's good enough.
So for the dynamics for fixed point, if E is not a lambda, then this one it won't terminate.
Exactly.
Does that mean we need to restrict the expression inside fixed to always the lambda?
No. So this is fine here. So you can, you can write because we a language, that necessarily, terminate always. So you can write, extremely weird stuff. For instance, like yeah, something like that. So if you would make a step with it, you get the same thing again.
And how is the progress given is relative? Can you find this?
Well, you just are always in this case. You keep going. Yeah. So here you don't have termination anymore. So you might say like, well, this doesn't make so much sense to write. So you can also, write things that are may or may not be more interesting depending on. Let's see, running out of space. If you have lazy or eager natural numbers. So since we're on it, so here's a more interesting one. So so now it depends on, what your dynamics is for the successor. Depending on that, it might, terminate after one step. When you say like, okay, this is a value. Right, then you are done, it's a value. And now you have to live with having this natural number, which is not really a natural number. So that's what you get from lazy constructors. Or if it's, in a eager setting, then you would keep evaluating. Then you get, S of the, whole fixed point thing here, and so on and so forth. And then it doesn't terminate. So then you don't have a value that is like this infinite number. So this is exactly the difference from like lazy or eager constructors that you see here. So, and that's also like in Haskell, you can have infinite lists. You can define like that. Same way in an infinite list. And in ML, where you have like eager constructors, can't do that. But that's a side remark. So sometimes, depending on the definition of your language, it might be interesting to have fixed points that are not functions. Okay, good. So now I want to, are there more questions about PCF? So this is really just a tool, you know now what it is. And from now on, whenever we want to discuss like a new language feature or like, some new concept, we can use PCF because it's like, the smallest language that is kind of interesting. So you have already most of the issues, in there that might come up. You have constructors, you have non-termination. So most of the things we want to discuss, we can talk about in the setting. So first thing I want to do is maybe clean the board a bit. And And then I want to talk about evaluation that I mentioned in the very first lecture. Also called big step operational semantics. So this is like a different way of, equivalent way of defining the dynamic semantics of our language. Yeah, so let's just say of defining the dynamics. So why should we go through, two different ways of defining that? Well, you will see next lecture one very good application for that. So sometimes if you want to prove something, about your language or about programs in general, it is kind of like important what semantics you have, and what you want to prove might be very difficult for evaluation dynamics and easy for structural dynamics. For instance, type safety. It's much better to work with structural dynamics to prove type safety than with an evaluation dynamics. It will make it much harder to formulate what type safety is and how to prove it. And I can explain why in a sec after you've seen it. So it's also kind of like, so my favorite semantics is evaluation dynamics. It's sometimes also called natural dynamics. And in the first lecture, you kind of like, somebody also like said like, yeah, what do we do first? And you kind of like hinted to, somebody said like, oh, well, we evaluate, E1 to a value or something like that. And that's kind of like the style of the evaluation dynamics. So the judgment looks like this. Yeah, so that's why it's called a big step. It only makes one big so, and the meaning is expression evaluates to value v. So there are no intermediate steps here. So the rules so if you already have a value, well, you don't do anything, you just return it. If you have something that's potentially not a value, and you want to find out to what value it evaluates, evaluate E, get something and then return the successor of it. Which seems to be nice and simple, only one rule for successor. So the lambda is still a value, so we don't have to do anything. Just return it. So what else do we have? The zero test. So what do we do here? So first we evaluate E, obviously. So by now we get a value right away, which is good. So maybe it's 0. So if we get 0, well then we have to evaluate the E0. So we do that. And then we maybe get V0, and that's what we just return. Nice and simple. Where E might evaluate to the successor of a value, and then we have to basically evaluate E1, but have to plug in this predecessor V for X. And then return the result. So 2 more. So we do the fix here. Forgot the type tau x e. So this is supposed to evaluate to some value v. If what? We have to, we basically want to evaluate E, right? But then we have X in there again that we don't want to deal with, so we have to substitute. The only thing we can ever substitute for X is the fix itself, so why don't we just do that? Good. So now let me remove this part here to squeeze this in. Only thing missing is the function application. So what do we do? So first we evaluate the E1, and we hope that this is going to result in a function, in a lambda, and then we evaluate the E2. Get some value V, and then we have to evaluate the function body. That's the third thing we have to do. E. Oh yeah, let's call this V2 here. And this is what we want to return. But of course, have to substitute for x the argument. Which was V2. Yeah, that's the third premise. Sorry about that. These three. That's it.
In the fixed case, the value will be a function type, I guess, right? I mean, what do we say values are?
Oh yeah, right. I didn't define what the values are. The values just, stay the same as before. So let's assume, we have the eager version. And usually the fixed point is going to be a function, but the same is true depending if you're going to do like eager or lazy constructors. But here I already decided to do the eager one, right? Because otherwise I would just return S of E here. So in our case, so what are the values? So 0 is a value. S of V is a value, V is a value, and the functions are values.
Isn't value like the thing where you have this big space of expressions and you carve it into these are final states and these are not final states?
Right.
Right? The ones that are final states are the ones where you get that judgment, this is a value.
Yeah. And this stays the same here in this case. It's just, a different viewpoint. I mean, here you have like, you jump directly from an expression to another expression, and it happens to be that this expression is always a value.
So, what's the difference between this evaluation and like step star or like the clean closure of the step?
Yeah, here you don't have a notion of
Step star, you can decompose it into single steps.
right.
This, it doesn't give you that kind of information.
Right, it doesn't have,
You have no idea how long it's been.
exactly. It's just like, it relates expressions to values. It's just like a relation, and there's no,
You don't know
yeah,
how it gets there.
right, exactly. There's no notion of a step, and that's
In operations, it's just like you're just assigning values to things.
right, exactly. You assign values to things, and that's exactly what I want to talk about today. So how can you introduce a notion of cost into there, and what's a decent choice for doing that? But before I do that, I want to point other things out here. So, for instance, we had this example. Where is it? Here. yeah, that just keeps going. So what happens to this example there in the corner with our evaluation dynamics? What can we put there?
So it doesn't terminate.
Exactly, it doesn't terminate. So
There's no value.
there's no value.
Because value means final state.
Exactly. So if we put some nonsense, so maybe successor of some function, we also don't have anything. So it's the same judgment in both cases. So this is exactly why what I said, like the structural dynamics is better for type safety, because this dynamics does not even distinguish things that don't make sense and things that don't terminate. It just for both cases it just says like, oh well, I don't tell you anything about it, and that's why it's not such a good fit for the type safety. But it is useful for other things, as you'll see. And I would argue, it has fewer rules, as you can see, and I also find it like very natural to specify it. And usually, if you ask people, if they are you tell them a little bit what you're doing, and I always do this when I teach this course and try to figure out what the operational semantics is together with the students. Most people come up with something like that, as opposed to the structural ones where you do like the small steps. So it is kind of, I think, fair to call it natural dynamics. Okay, of course it relates to structural dynamics. So, where's my... So if I have an expression E, and I make a few steps, and I reach a value, so what is true then for the evaluation dynamics? So let me be a bit more efficient. Should evaluate to the same value, right? And that should be true if and only if the other thing is true. And that's the case, so we can prove that, yeah, by rule induction. And it's a bit more complicated than you might think, because you might have the idea, if you go like from the structural dynamics to the evaluation dynamics, you could do something that says like, oh well, I do like induction on the number of steps. But then what you'll find is that you have to argue about the case where like, this is not a value, but an expression. So you have to do, a little bit more work than you think if you want to prove that. So that's a good exercise, but it's not as easy as you might think. Yeah, because there's no correspondence of these intermediate things you get here when you do like the individual steps. There's no correspondence up here. So, and this is what you have to overcome. So. Good. Next, I want to talk about the cost dynamics. So are there any more questions about the evaluation dynamics? So, okay, yeah, so this actually something that came from you already. So in the structural dynamics, there is a natural notion of cost, the number of steps. But in the evaluation dynamics, we don't have that. And how can we, introduce the cost measure, and what's a good idea? So what I want to do is I want to change it a bit. Let's see, write it over here. Oops, big surprise. So the judgment should be something that's following. So we're going to now say well, E evaluates to an expression E evaluates to value V with some cost N. Okay. And so, maybe you have any suggestions what this should be? Yeah?
Well, it goes down to step star, so you can just measure step star.
Exactly. So you could just say well.
Structural dynamics.
Yeah. So exactly. So just the number of steps in the structural dynamics. So that's something you could do. So you could
get cost and evaluation dynamics by sending it over to structural dynamics.
Right. Exactly.
Taking a measurement and sending it back.
Well, that's not what we're going to do, because that would be weird. But that's the idea. So that's what we want. So that's exactly what
But then what's
I'm going to do.
dynamics? If all this is just mapping to an underlying step,
Right.
and then evaluation dynamics
Well, you lose some information for the non-terminating ones, but that's only one thing you can do. So you can define different cost. Nobody, forces you to do it like that. So, but it's an important thing to, you had the right idea right away. So you want to justify the cost by some, more low-level notion of computation, and then you want to somehow, justify that, the evaluation of at the high level relates somehow to it. So here it's kind of like, easy because like E stays at the same level. If you want to, like in my research, if you want to do it more realistically, you want to have like a cost level for your high level language, a cost model for your high level language that relates to the compiled code that's executed on the machine. And so then you have like a more realistic cost semantics, but you have to make this argument that this is the case, and we're going to see in the next lecture somewhat, when we come to parallelism, a somewhat like surprising result of that category. Yeah.
So I've never done this, but my intuition says, can do a syntax-directed attribute calculation kind of thing, like the if, right? The cost of computing the E enters the formula.
Yeah.
Then you add 1 maybe to compare with 0.
Right.
And then what in one case you get the max of the so
Yep.
you want to take branches.
Exactly. So that's another thing you can do with the cost semantics. So what you're suggesting, I think what it amounts to is you just count like the size of the derivation of the evaluation judgment. So how many rules did you have to use to derive the judgment? That's another, valid way to, account for the cost. And here it's not the same, but it's already very close to this n. So, and we can assign cost. But you can also count something, so you're all focused on, some like notion of time here. Because these are both kind of good notions of time that are, asymptotically equivalent, both of them. But you could also say like, oh, well, I want to measure space. And then you can introduce at the lower level, some, notion of space, and you want to measure that at the high level. You can also say, well, I want to, for some reason, count something very specific. I have like an operation in my language that, sends something over the network, and I want my cost semantics to just, count for the amount of data that's sent over the network. All this, is possible. It's just always, so people always say like, oh, well, it's like with these, cost semantics, is that realistic? Well, you have to make the argument. But of course it can be very realistic, yeah. Okay, so let's do this. So, yeah. Yeah.
Where are you going with Hoffmann? This theorem, before you go input there, you just go star.
Yeah.
I mean, isn't that what the arrow with star means? I mean, what's the content of this?
Right. Now the content is that you have the same n here and here. I mean, so that's something, we don't have yet. Oh, previously it didn't, it said at least you get the same value in the end.
Between doing what and what?
Oh, between.
Taking lots of steps and the other one is taking lots of steps.
Exactly, but they arrive at the same value. I mean, if you would be unlucky, yeah, right. But I mean, if you would have like a different value here,
But they're both doing the same thing.
Yes, but that's what we want. We don't want them to do something different. So that would be bad. Right? I mean, if you...
I guess I don't know the definitions of the arrows then.
What is the difference between the two types of arrows?
Oh, okay.
Oh, between...
Star just meant at least 2.
Wait. Okay. So that's how this looked before, right? At the bottom here, we have a statement that talks about the evaluation dynamics, the small step thing we defined, okay? And up here, talks about a completely unrelated thing, which is like the evaluation dynamics we defined there, right? So that's what it says. And now, I mean, maybe, so the problem was because I erased that, so let's... Right, so, okay, so let's use it again. So, I mean, this is equivalent. So in the first step, right? So that's equivalent to say like, okay, so you have this if there exists an n, might be 0. So that, and so now what we want is to define, to change this judgment so you get the same n there. So that's our goal.
If I want to implement this, so having two functions, so one function is taking one step to get evaluated, and another function is taking multiple steps but coming up with same. That's what we mean by having these two kind of dynamic instances.
Wait, so I mean, for now, you can just say like, well, that's just like a different way to, define the same thing. Yeah. So, why? Well, so for now, just say like, okay, accept that this is possible, and next lecture I'll show you a good application for it. Yeah. Already, I would say evaluation dynamics is really nice if you want to define, some cost model, and you'll see why in a second when we do it now. Yeah.
Define the arrow in the left-hand side.
Yeah. So. Well, let's maybe use the plaque. So you always have E in 0 steps to E. Yeah, it looks very similar to the star one. And if you can make a step from E to E prime in the small step semantics, and you can go from E prime to E prime prime in n steps, then you can go from E to E prime prime in n plus 1 steps. So, yeah, some are very happy about that. Yeah, good. Okay, yeah.
Actually, I was asking about the other arrow.
Oh yeah, the other one. Yeah. That's exactly what I'm going to do now. Yeah. Okay, so let's start with the axioms. So what should I put here? 0, exactly. So now it's already different from counting the number of rule applications. And where's our axiom? Did I forget to write that? No, it's right here. Yep. Same thing, also 0. So, yeah, this one up here. So here we have, of course, some cost we can't influence, we get, but then we have to, assign some cost to the conclusion. Yeah, so n or n plus 1. So, well, that's unclear. So now we have to remember, it's also unclear to me, honestly, so now we have to remember what the rules were for the successor, right? So we first do the inner one, and then when it's a value, we're done. We don't make further steps, so it stays n. Yeah.
So the computer will have to do a consequence.
Right, so I'm not saying that's a realistic measure when you run it, but yeah, that's a bit of a so, but it's interesting. So what you're saying is, like we said, like, okay, so this structural dynamics has like a natural cost measure. What you are saying that this is probably not a good one because it shouldn't be zero. At least, you wanna, I mean, with that, if you look at these two rules, right, if you, evaluate like the number 100, like S of S of S of S of S, it has cost zero. Is that really, good? Well, at least you want to look at it, before you return it or something. So that's arguable. But we set out, with our theorem to get this. So that's what we're doing now.
Depends what you are. Actually, I say what you did is correct because of the purpose here.
Exactly. Exactly. Yeah, but you are saying, well, is that a good cost measure or not? Well, I don't know, probably not. Yeah, but let's go with it. So here, now we have what? So we have given n1 and n2 in the premises. So now, what do we write down there? So now actually we get some costs, right? Because we evaluate first, the E, and then we evaluate the, well, then we make a step, and then we evaluate the E0. So that's the order how that works. So let's say, n, and add another premise here, n equals n1 plus n2 plus 1. Here it's the same thing. That's easy. N equals n1 plus n2 plus 1. So what about the fixed point? So here we have n, and what do we put below? N plus 1, right?
I said minus.
Oh, minus? No. That would be a very good deal. Yeah, you would get an extremely good deal with a fixed point if you put minus 1.
Why not n plus 2? You don't count substitution as a minus 4.
Well, we count it, but it's just one step. So where's the rule again? I think I'll have it somewhere. Yeah, here. So with a fix, you see, you just do one step, and you don't. Again, it's a question like, is that like a fair measure? Because you might even substitute it like multiple times, because there are multiple occurrences of this variable x here, and why only count one for it. But the beauty of this is, if you don't want this theorem, you can define different cost semantics that is more appropriate for whatever purpose you want to have it for.
So why is that n plus 1?
Because you make one step here, right, and then you make further steps. So here you first make further steps, and then you have to add 1 to it. Yeah. So, and then the last one, the application. So it's and 3. Oh well, the names are not ideal. And 2. So that's like the order, at least. And then the cost here you have is n. And what do you want? N is n1 plus n2 plus n3 also plus 1 at least plus 2.
And 3 includes that plus 1 and 3. Brings to the value.
Let's see. No, you have one x. Yeah, no, I think you have one more. Yeah, and you would have to prove the theorem actually to know if it's really correct. But I think you have one more because you make, if you look at the rule, well, if this is a lambda, so then you make the step with a substitution, right? And this you have to, I think that's where the plus 1 comes from. Okay. Yeah, that's just, one example of, how you can justify cost semantics. Okay, want to count the steps in the structural semantics. And next time, tomorrow morning, we're gonna look at parallel computation, and we're gonna define also the cost semantics for it, that you will say like, oh, that's completely unrealistic. That doesn't tell us anything, and then I'll show you a theorem that, tells you it's not so unrealistic. And and then you see, hopefully, the use of like this, evaluation dynamics and cost semantics. Yeah, question?
Since we have to evaluate the value before we know the cost, because you kind of have to run the program and then you have to measure how long.
Yeah, exactly. It's like benchmarking. It's a dynamic notion. So in my research, and that's maybe what you're thinking of, you can also, now you only get information in the type systems. We look in about what the result of the computation is. So it's, a natural number or it's a function or whatever, but you don't get any information about what cost it will be. So this kind of cost component here is kind of like oblivious to the type system. And it doesn't have to be like that. So you can develop type systems that tell you something about this cost, and then you can prove theorem that says like, well, the bound given by the type actually corresponds to the cost you have when like running it. That's given by the cost semantics. That's something you can do.
I didn't completely get that. You said you need to benchmark to get the cost, right?
No, I think the question was, so this is it's a bit like, benchmarking. You run the code and then you see what the cost is. And yeah, that's true. But I'm saying like you can go further than that. You can now also define a type system that, talks about the cost. And that's what my research is actually about. Yeah. Okay, good. So if there are no further questions, so then we're ending. Oh no, it's not even on time. Sorry, I thought we're 10 minutes late. Okay, so then see you tomorrow.